Hello, and welcome to Part 11 in the module that provides a case study of Gang of Four patterns. In this module, we presented patterns in the context of our expression tree processing application to do a wide variety of different things to make the design easier to understand, evolve, and maintain. We started off by talking about various patterns for tree structure and access, the composite and bridge patterns. We then talked about various patterns for tree creation, such as interpreter and builder. We then talked about various tree traversal patterns, things like iterator, prototype, and visitor. After that, we talked about patterns for creating commands and factories, things like the command pattern and the abstract factory pattern and the factory method pattern. After that, we talked about patterns for ordering commands to obey the appropriate usage protocol, and that was the state pattern. Then we talked about patterns for structuring the application control flow, the reactor pattern and singleton. And now, finally, we're going to talk about various patterns that encapsulate algorithm variability. The purpose of these patterns is to simplify the processing of multiple operation modes, our succinct mode and verbose mode that we've been covering throughout this particular module. We're going to be applying the template method and strategy patterns to do this. And these patterns, as you'll see, help to support controlled variability of steps in an algorithm. People sometimes think that object-oriented design is not about functionality, it's not about actions, it's only about structure. And that's not true, but what is true is that we want to be able to deal with the algorithms in a way that follows naturally from the structure. And the discussions we'll have here will help to illustrate that particular point. So what are some of the design problems we're trying to wrestle with? Well, to start with, some of the goals we have are to minimize the effort required to support these different modes of operation. The so-called verbose mode, where users type commands in order to be able to format and evaluate and print and quit and so on to interact with the program, as well as succinct mode, which is basically a glorified command line calculator, where you get a prompt, you type an expression using the in-order format, and you get an answer back. What we also want to be able to do is make sure that we don't tightly couple these different operation modes with the overall program structure. We want to make sure it should be easy to change our minds and add new different operation modes in the future. We also want to avoid many of the limitations that we had discussed much earlier in this module pertaining to algorithmic decomposition, where we had programmed ourselves into a corner. Any small changes we make would ripple through the code, breaking encapsulation. We didn't do a very good job of modeling the domain, and we basically structured the solution around particular details of the algorithm, which made it hard to evolve and change later. We want to avoid trying to do that in this case. So it's going to turn out we'll have two different solution approaches to evaluate, starting with the first one, and they both end up trying to encapsulate algorithm variability, but they do it in different ways. The first one will involve implementing the algorithm once in a base class and then letting subclasses derive variant parts. So to illustrate how this works, you see we have our event handler hierarchy. So we have event handler base class, and then we define the ET event handler or expression tree event handler subclass, and it defines a number of methods. One of these methods is the handle input method, which is what's used to connect to the reactor when input events show up. And this input method has four so-called hook methods. And in fact, the handle input method is what's called a template method. It defines the steps in the algorithm and writes them down in an orderly way. The template method defers to the hook methods in order to be able to allow controlled variability of the various processing steps. And we'll talk about this particular algorithm. As you can see here, the four processing steps include prompting the user, being able to get the input from the user, making a command from the input from the user, and then going ahead and executing those commands. Now, the way we're going to solve this problem is we're going to allow subclasses to come along, inherit from the ET event handler class, and then fill in different processing behaviors for those steps in the basic template method algorithm. And it does this by overriding the hook methods. So for example, here's an illustration showing how we might override the make command method in the verbose expression tree event handler, and how that compares and contrasts with the succinct expression tree event handler. For the verbose event handler's method, the hook method that's customized, it goes ahead and just creates one command, whatever corresponds to the user input. Conversely, for the succinct mode method, it goes ahead and creates a macro command, which we've looked at earlier in some of our discussions about various factories and commands. And what the macro command does, if you recall, is it goes ahead and creates multiple commands. It creates a command for dealing with the format, which will be perceived to be the in-order format. It then goes ahead and makes an expression tree using the input from the user, and then finally turns around and evaluates it using post-order traversal, for example, in order to get the yield of the expression. So we can have controlled variability to modify things. We could also change the way that the user is prompt. We could change the way the commands are executed. We can change how the input is received, and so on and so forth. And all these things are done within the context of the template method. Here's an illustration of the ET event handler class interface. This provides an abstract interface for performing the algorithm that's associated with the expression tree processing and the application therein. As you can see here, we have the handle input method, which is the template method. We have a factory that's used to make the appropriate type of handler, event handler, for succinct mode or verbose mode, for example. And then we have the various hook methods, which, as you can see here, are defined as virtual methods, some of which are pure virtual, some of which are virtual, and which have default behaviors associated with them. From a commonality and variability point of view, this class provides a common interface for handling user input and being able to deal with the steps for performing the actions requested by the user. From a variability point of view, you can inherit from this class and then override some of the hook methods in order to have controlled variability of some of the steps of the template method that we have. The way that you arrange these particular groups of classes and methods is given a name. In the Gang of Four, this is called the template method pattern, and it's a class behavioral pattern. The intent of template method is to provide a skeleton of an algorithm within a method and then define some of the steps that can be deferred to the subclasses. You would apply this pattern typically when you want to make sure that there's certain invariant activities that an algorithm does, and then let the subclass override those as it sees fit, if it sees fit. You might also want to be able to do this to localize behavior in a class to increase code reuse, because you can fix the steps in the algorithm and you can make it clear what goes on there. And you might also want to be able to do this to control the way in which subclasses either have to or choose to extend the various capabilities. There's a structure diagram here that illustrates how this pattern is described in the Gang of Four book. As you can see, you have a base class that's the abstract class, and it defines at least one method that's called a template method. And the implementation of that template method invokes a sequence of so-called primitive operations, which I've been calling hook methods. I think that's an easier name to understand. And then you subclass from the abstract class and make a concrete class. And the concrete class can choose or not to override those methods, those primitive operations, those hook methods, in order to vary the way in which the template method behaves via the subclassing. In our particular example, we have the ET event handler, which is the abstract class, with the handle input method, that's the template method. And then we can subclass the various types of succinct and verbose event handlers and fill in and override some of those methods. So let's take a look at how we might implement this particular pattern in C++ in the context of our expression tree application. We're going to allow subclasses to be able to override some of the steps in the algorithm. So here's just a little bit more easier to read illustration of the handle input method, which is the template method, which calls the various hook methods in a certain order. And then we can come along and inherit from that and then define the way in which the verbose event handler's make command method works, in which case it goes ahead and makes a single command, and contrast that with the way that the succinct event handler's hook method works, which makes a macro command. Likewise, we can also illustrate how the factory we've defined might select to choose and implement and instantiate the appropriate choice of event handler, either verbose or succinct, based on options that are passed in on the command line. This is not the only way, or even the best way for sure, of defining a factory. It just illustrates a way to get this made. You could do other mechanisms by integrating this back into our abstract factories we discussed in previous parts. You might have a pointer to a function you could use. Lots of different ways to do it. So some of the consequences of applying this pattern: it enables inversion of control, which is the Hollywood principle. Don't call us, we'll call you back. It also promotes code reuse because you can fix the steps of the algorithm in one place and then make it clear how to extend them in a very systematic way. It lets you decide how to enforce the various overriding rules, under what circumstances to allow things to be overridden, and so on. But there are some downsides. You have to subclass from the base class in order to perform the variation. And we'll see in just a minute when we talk about the strategy pattern how this issue can be overcome, which is an improvement oftentimes. There's a number of implementation considerations to keep in mind when you implement this particular pattern. One question to come to terms with is, do you want the template method to be virtual or non-virtual? My typical preference is to make the template method itself virtual, because if it turns out you have to vary some of the steps of the algorithm, you have a way to do that through subclassing. If you do not want the steps of the algorithm to be varied under any circumstances, of course, define the template method to be a non-virtual method. Another question might be whether you have a lot of primitive operations or hook methods or just a few. If you have a few, that may provide only a couple of places of variability for subclassing and for users to override and customize. If you have many, many, many of them, of course, it can be difficult to understand what your algorithm is doing, and it may be very difficult to verify and validate that it works properly for all the combinatorial number of different ways of being customized by subclasses. There's also some other minor design questions. What do you call the methods, the hook methods? Are they make? Are they do? It's up to you. I typically follow a particular convention. I like to use the make prefix, but that's just my personal preference. Lots of places where these patterns are applied. This pattern is applied. It's applied a lot in user interface toolkits, ET++ and interviews going way back in the day, AWT for Java more recently. We use it very frequently in our ACE orb for various capabilities to extend and modify the way the internals are implemented and how they can be extended. And it's also used in parts of Android, especially in the activity and service classes, where it's used to be able to have controlled variability in terms of how you handle lifecycle operations for creating and pausing and deleting and stopping and starting various activities and services. Now that we've covered template method, let's explore an alternative design approach we could use to encapsulate algorithmic variability. This particular approach is going to implement the algorithm once in a base class and then let pluggable strategies define the variant parts. Now, part of this is going to look very similar. We're going to start off with a base class ET event handler like we did before, and we'll have the same template method that we used before. But things get a lot more different from here on out. What we're going to do is we're going to inherit a single class from ET event handler, and we're going to call it the strategy ET event handler. And what this class is going to do is it's going to have strategy objects that will be composed into an instance of this class in order to control the various steps that the algorithm takes when it is run. Now, to make this even more interesting and to show the diversity in which you can implement the same pattern with many different mechanisms and techniques and language features, we're going to implement the variability here not so much with subclassing, but instead through template parameterization using C++ parameterized types. You could do some similar things with Java as well. And so what we'll be doing is we'll be defining the strategy ET event handler class as a parameterized type where we can plug in different strategies in a very flexible and extensible way. So what we'll do here is we'll plug in these different strategies, and then the hook methods that we define as part of the template method will simply turn around and forward to the appropriate strategies that were plugged in when the object was created through the constructor. We'll show you some examples if that seems a little bit abstract to make it more concrete. So here's an example of some of the strategy template parameters that we're going to use in order to be able to customize and modify different steps in the overall template method algorithm. we're going to have these different template parameters. We're going to have a make command strategy. We'd have an execute command strategy. We'd have a prompt the user strategy. We'd have strategies for anything we need to do that might vary. The expected signatures we have would include a make command method for the make command strategy and an execute command method for the execute command strategy. From a commonality and variability point of view, we are having common method signatures that define the types and the return values that we're expecting to have for templates that are plugged in, so they have a common interface. And from a variability point of view, you can easily change the way in which these various behaviors occur by plugging in different templates to the strategy ET event handler parameterized type. By the way, just a quick note, it's a little bit of shame that the pattern from the Gang of Four book is called the template method pattern, and C++ has a feature called templates. Ironically, these are not the same concepts. They are vaguely related very abstractly, but template method is a pattern that you use to inherit and override various hook methods. Templates are parameterized types, which you can use to have generic programs and generic containers and algorithms that you can customize their types in a flexible and composable way. The way in which we combine these things was an illustration of a very popular Gang of Four pattern called strategy, which is an object behavioral pattern. The intent of this pattern is to define a family of algorithms, encapsulate each one, and make them interchangeable to let clients and algorithms vary in a number of different controlled ways. You might want to apply this pattern under a number of circumstances. If you want an object to be configurable with one of many algorithms or algorithm parts, and all the algorithms can be encapsulated in a common interface, and one interface can cover all of the encapsulations. Now, here's where things get interesting. So the structure diagram that's illustrated on this slide illustrates the Gang of Four representation in the book of the strategy pattern. And in this pattern, there is a base class, which is the strategy with one or more methods that are the strategy interfaces, methods. And then you use subclass from that to make various concrete strategies, all of which have the same interface. And then connected to that is something that's called a context. And the context is where you store state and other types of information that's needed in order for the strategies to do their thing, especially for situations where the one-size-fits-all interface for the strategy class and subclasses doesn't quite capture enough diversity and variability. So you can kind of push those issues up into the context. Now, our particular use of strategy for our example is somewhat lobotomized. We don't use inheritance. We use parameterized types. So in some sense, we have concrete strategies that are template parameters that we pass to our strategy ET event handler parameterized type class in C++. But keep in mind, it's still the strategy pattern. If you read the Gang of Four book, this is listed as one of the variants of the pattern. So let's take a look at how we might actually use this particular variant to implement our expression tree processing app. What we would do is we would define the strategy ET event handler as a parameterized type, and we would give it a bunch of different kinds of parameters. The ones I'm going to focus on here are just the make command strategy one, and I threw in execute command strategy just to illustrate how that would work as well. So we define those as part of the parameterized type. We inherit from ET event handler, so we get its template method and its hook methods. And then we go ahead and pass in the various instances of our parameterized types to the constructor of this class, and we would stash them away in data members of the same name that would keep that information for the various hook methods and other parts of the class to do its thing. Notice, by the way, this interesting combination of template method and strategy. We're actually making them work together, which is even more interesting when we combine them with parameterized types. We get lots of different commonality and variability and high pattern density all in the same abstraction. What we can then do is the hook methods that we've got defined on our strategy ET event handler could then turn around and forward to the appropriate strategy objects that were configured in the constructor based on the templates that we'd used when we instantiated this particular class. And I'll show you a bit more of that in just a second to make it a little bit more clear. Here's an example of something that we might have as a macro command strategy. This is used as an argument to the template class, to the strategy ET event handler parameterized type. And you can see what it does is it's got a make command method that simply turns around and forwards to a configured command factory, which we could do in the constructor somehow, which then forwards down and makes a macro command from the input that's passed to it. And this, of course, will all get glued together at compile and link time, and then via the magic of dynamic binding, this thing will get called by the appropriate hook method by forwarding through the strategy instance. This, of course, creates a macro command. Here's an example of how we might have the factory function called makeHandler that will define, in this case, for this particular subclass, the strategy ET event handler. And it takes the verbose flag, and then based on whether it's verbose or not, it goes ahead and creates a strategy ET event handler instance that is either configured with the command strategy template if we're doing verbose mode, or the macro command strategy we just looked at if we're doing succinct mode. And I've left out some of the details, but you basically get the idea how you could do this in a very plug-and-play-like way by defining different command strategies, different types of strategy objects, and then plugging them in through the magic of parameterized types. So some of the consequences of applying this particular pattern: very flexible, easy to reuse, lots of small pieces. You can plug and play and mix and match very readily. We don't show it in this particular example because we're using more static binding with templates, but if you use a more dynamically bound approach with a little inheritance and a little bit of dynamic binding, you can plug in the strategies very flexibly at runtime and change the behavior of the objects on the fly. There are some downsides. You end up with lots of strategies potentially, and there could be a little bit of communication overhead due to some indirection. If you're not careful, the strategy interface may be too narrow to cover all the different kinds of things you need to do. So you might consider either dealing with the context to store some of the information, applying adapters. There's all kinds of little tricks of the trade you can apply to make this work in practice. The other issue, of course, is if you end up with programs composed of many, many strategy objects, there's always the potential for semantic incompatibility when the different strategies are combined together in unexpected ways. A good way to deal with that, of course, is to apply the abstract factory pattern in order to control the way in which the strategies are created. There's a number of implementation considerations. How do you exchange information between the context and the strategy? We actually just didn't use the context at all. That's not uncommon to ignore the context. In practice, though, you might have to think about that. Do you use some kind of method-based interface, a setter-getter interface? Do you let the strategies peek up into the context and access its fields directly? There are pros and cons of each approach, of course. Another implementation consideration is whether or not to use this static binding approach like we've done here that uses parameterized types as opposed to dynamic binding in order to plug in different alternative ways of doing things. By the way, the use of the parameterized types is sometimes called policy-driven design in C++, and it's very, very widely used in the C++ standard template library. Things like functors, for example, can be viewed as little strategy objects that you can plug into algorithms or containers in order to vary their behavior in systematic ways. There's lots of known uses of this pattern. If you take a look at the Gang of Four book, they give an example of using it for breaking paragraphs into lines and doing hyphenation and so on. There's examples. Interviews does some of this and some of its text formatting behavior. There's uses of this in compilers for register allocation and optimization. It's used in ET++. We use this pattern very, very heavily in the ACE orb to change the way in which the various mechanisms for concurrency and synchronization and transport protocols, connection management are handled by the middleware. So it's a widely used pattern. It's probably my favorite Gang of Four pattern. I use this pattern almost more than anything else, largely because I'm always trying to find a way to build systematically reusable infrastructure that can be tuned and tailored for different use cases efficiently. It's interesting, by the way, to compare and contrast the strategy pattern with the bridge pattern. They both look very similar if you look at their structure diagrams. There are some subtle differences. The strategy pattern is a behavioral pattern. The bridge pattern is a structural pattern. The bridge pattern has an interface or an abstraction that's used to forward to the implementer hierarchy. In contrast, the strategy has a context, which you typically don't access if you're a client, whereas you would access the abstraction from the bridge. But they also have a lot in common. And in fact, it's not unusual to find pattern compounds of bridge strategy in practice. Let's take a minute to compare and contrast strategy with template method, because they're basically alternative patterns from a pattern language point of view or a pattern sequence point of view. Strategy typically can be used to provide a more clean black box separation. You don't have to know as much about the innards, you just have to know its interface. And it also, when used properly with dynamic binding and inheritance, can be used to allow objects and strategies to be modified on the fly, which is often more flexible. You can also mix and match features in a very fine-grained, composable way without a lot of overhead. But there are some downsides. There's some forwarding overhead when you use strategy, typically. You may also end up with lots and lots of strategy classes. The surface area can be very large, which is one reason why I chose to use the template version to illustrate my example, because if I used the inheritance version, it would have been a lot more pieces of code to illustrate in a short presentation. Template method has some pros and cons as well related to strategy. No explicit forwarding is typically necessary. You're just going in direct through the dynamic binding part of the template method, hook method that's being forwarded to. It can actually be a little bit easier to use for small use cases. If you just have one method or two methods that are hooks in your template method and they don't change a lot, not too hard to work with. In fact, you can think of factory method in some sense as being a bit like a template method in certain cases. It's just a very limited use of the template method. There are more downsides, however, with template method than with strategy. There's a close coupling between the subclasses and the base class. By using inheritance hierarchies, you make more static, more lexically dependent interactions in pieces of code and how they work together. Whenever you start using inheritance, you have to be a little careful that you don't get carried away and end up with deep inheritance hierarchies that are very brittle and hard to evolve. You also have to be careful with the cross-combination of different capabilities. If you have a template method with 5 or 6 hook methods, each of which could vary from 2 to 5 ways, there's a combinatorial number of different combinations of subclasses you might have to consider to cover all the different cases. In those environments, strategy may be a much easier way to go, much more pluggable, which is also one reason why you find it used in places like the C++ standard template library, because it's easy to plug and play that way. As a rule of thumb, people who build black box frameworks tend to use strategy-like composition. People who build white box frameworks tend to use more of a template method form of subclassing and extensibility. And many times people will combine them both. So keep on the lookout for ways in which we combine them, just like we did in our example. They often work better together than they do separately. So to wrap up this discussion, the strategy and template method patterns are really alternatives or duals that allow us to simplify some of the processing in our expression tree application, in particular handling different operation modes. And this pattern allows us to be able to avoid some of the limitations that we'd seen earlier with algorithmic decomposition, where we programmed ourselves into a corner, where it was hard to make changes without ripple effects that went through all the code in cascading ways. We've covered a lot of material in this particular module. And as we wrap up, I'd just like to kind of step back and summarize some of the things that we've learned. As a general rule, pattern-oriented ways of developing software, like our expression tree, are an improvement over other approaches, especially the algorithmic design approaches. Why? Well, one reason is that they end up being much more modular and extensible. Our original algorithmic design that we'd looked at was very hard to evolve. Any small change had a cascading rippling effect throughout the code. There wasn't a lot of encapsulation. The pieces were tightly coupled together. In contrast, we ended up with very modular solutions. It's easy to add new capabilities. It's easy to add new nodes. We can add new commands. We can add new types of traversal, iterators, and so on and so forth. We can add new types of operation modes, and they're all very localized and contained. We also have done a more effective job of modeling the domain. The design that we came up with for the pattern-oriented solution looked and felt a lot more like our deeper understanding of an expression tree, whereas the algorithmic decomposition was kind of hacked up just to get things to work. It's also worth noting that the object-oriented approach could potentially end up with less overhead in terms of the space allocated for the nodes. If you recall, each of the nodes we had before for the algorithmic decomposition had to assume the worst-case space utilization, even for the leaf nodes, which are the ones that don't have any children. In contrast, with our pattern-oriented approach and our use of the composite pattern, the leaf nodes didn't really take up any more space than they needed to, which makes them more parsimonious. There's a nice article written by Andy Koenig a number of years ago, appearing in his book, Ruminations on C++, that gives another C++-oriented view of how to implement an object-oriented expression tree. So if you have a copy of that book, you might go back and take a look and see his approach and compare and contrast it with our approach with a heavy pattern emphasis. There's some other things to keep in mind as well with respect to the improvements of pattern-oriented approaches versus conventional approaches. One thing you see in our design over and over and over again was this concept of high pattern density. If you look at the various interaction diagrams and the class diagrams that we showed, there's lots of classes. And all these classes, for the most part, play some role in some pattern, often roles in more than one pattern. And so when you take a look at the surface area of the design, you can understand the rationale for why things appear where they are. Another thing that patterns help us to do is they help to explain to people what all these classes and methods do. Quite frankly, if you didn't understand the patterns and someone dumped this kind of a solution on your lap, you'd probably be a little bit taken aback at first because it just looks like a sea of classes and a sea of relationships, and it's hard to navigate at first. Once you understand the patterns, however, each piece fits together. You can explain why it's there. You can talk about the alternative design structures you considered and rejected. You can compare and contrast the different alternatives, look at the ways in which they resolve certain forces better than other ways of doing it. And that's a great improvement if you're trying to document solutions and explain them to your team, especially over long periods of evolution and maintenance. When I give these type of assignments in my courses here at Vanderbilt, I'm working with people who are typically second semester sophomores, first semester juniors or so, many of whom have never implemented more than a couple of hundred lines of code at a time. And by the time we implement the whole full-blown expression tree processing app, they've written 3,000 to 5,000 lines of code. And that's daunting at first, but when you understand the patterns, it all just kind of flows together very seamlessly. Something else we get with patterns is the ability to be able to keep the design fixed and then be able to realize the design in different languages. So for example, almost everything I've showed you here could either be done in almost identically the same way with C++ or Java. There are some minor syntactic and semantic differences in those languages that would make the implementations a little bit different, but by and large, they would realize the patterns in very, very similar ways. The Java solution would be a little simpler because we wouldn't have to wrestle with some of the issues of memory management, which caused us to use our good friend, the bridge pattern, over and over again throughout the designs. You can take a look with respect to different ways of implementing these designs in these patterns in terms of Java versus C++ at the link down below, which gives you a nice overview of different examples of many of the Gang of Four patterns and other patterns implemented in different languages. And you can see quite easily how it expresses the design commonality. So I hope you've enjoyed this discussion of the Gang of Four patterns, and I hope these will make you more effective as a software professional at becoming a master software developer.